So I'm sitting here with my mosquito electrical tennis racket thing that shocks the bugs. Have you ever seen one? Have you ever used one?
Yeah, where you have to press the two buttons at the same time, and then
this was just one button, but
I guess mine was safer than yours.
How would you describe how it worked? Like, I learned something after I used it that I didn't think about before I actually saw one.
So this is a quick question. Do you have one of the ones that has like an outer like little net thing? That's so like it's kind of like a mesh between, and then in between our rails.
So that's what I hadn't thought about, and it made total sense once I held one in my hands. And then, but if you would have asked me how it worked before I actually saw one, I would have just said it's a metal like grid connected to a battery, and then you touch a bug with that metal and it zaps it. But you said exactly the thing that I was kind of not shocked, but just kind of like, oh, I never actually thought about it, is that there's multiple grids, or like there has to be like basically you need to complete the circuit with the bug, and the bug has to touch two pieces of metal at different potentials to get zapped, right?
Right, yeah.
That's what I hadn't thought of. I thought it was just batteries connected to metal, and then you zap the bug with the metal. But that wouldn't work. Like you can't just have metal at some potential touch a bug.
No, that'd be like if you touched, a solenoid. A solenoid's a bad example because they have the enameled wire, but I'm trying to think of a case where I have touched.
Well, it's the joke with the kid in Jurassic Park. Like if they would have turned on the fence when he was on the fence off the ground connecting to parts of the fence at the same potential, he wouldn't have been zapped. He wouldn't have been thrown off the fence, right? Like the bird on the wire doesn't get shocked because it's all at the same potential.
That's the best example, but
yeah.
But then the eagle that hits two wires, he's dead.
He's zapped.
Yeah. Actually, so I didn't think about it until you asked me if I'd seen one before, and I was trying to think. I've seen two models, and the model that I had as a kid looked essentially like a tennis racket, but there was just like horizontal stripes on it, metal pieces, and that was it. No, there was no second layer of metal like on the I want to say the Z-axis, if that will make sense to you.
Right. They're like stacked layers.
Yeah,
so do you know how that one worked?
So my guess now is that you had an alternating set of positive and ground, positive, ground, positive, or positive, negative, however you want to think about it.
Yeah.
Rails. And then so all of the hopes that whenever you hit the bug, it would make contact with one of each and then complete the circuit.
Yeah. So that's what I was imagining. So like if you counted them, there'd be like 1, 2, 3, 4, 5, whatever, and so on wires. All the odd ones would be at one potential. All the evens would be at a different potential.
Yeah.
So that when it touches two adjacent wires, they're at different potentials, then it gets zapped. Yeah.
Yeah, I guess I never thought about it, but yeah, that's got to be, something along the lines of how it works.
And something I just realized, Lindsay and I it says on it, like, don't touch. Obviously, it seems smart to say that. But Lindsay and I like tested it. We're like, well, what does it actually feel like? Because I remember friends in college doing that, like being stupid and like zapping themselves with the bug zapper. And so I was like, I pressed the button and like tapped my kneecap, thinking that would be like a place that wouldn't really hurt that much skin wise. And I didn't feel anything. And then I touched my finger, nothing. And then Lindsay did it. She didn't feel anything. So now I'm like, oh, I need to touch both grids. I need to like get my finger in there to touch the other one. Because I was just thinking like, oh, it's not a big deal. Like you can just touch it.
So the bug must pass through then.
Right. Yeah. To get zapped yourself, I think I would have to stick my finger in it. Should I do it?
For the sake of our science podcast.
I mean, okay, this is another question. How much power could really be put out by this 2 AA batteries?
So if they're in series, it's 3 volts and probably a couple amps.
Well, actually, that's a bad. Well, I don't know. It's not like maybe it's a capacitor. Have you ever been zapped by a camera? Like, you take apart disposable cameras and like shock people with them?
I never did that myself, but I watched my friends do it.
So that's a much smaller battery, like a tiny, I guess it's probably 1.5 volts also. Maybe it's 0.5 volts, I don't know. But they have a capacitor in there, and that's what zaps you is. It charges it up and discharges quickly a lot of energy.
Right.
So maybe that's what's going to happen here. It doesn't feel like when I press the button it's charging anything, though. I guess it's just arming the circuit. Maybe the capacitor is always charged and ready to go.
Yeah. I mean, there must be. So now we're going to have to go get an oscilloscope. I'm going to have to go buy one of these, hook it up to an oscilloscope.
Yeah, exactly.
See what happens. But yeah, I mean, there must be. It could just be that is the capacitor itself, is the grid, the two grids.
Huh. Well, okay, so I can tell you this model has 3 grids. It has 2 on the outside and 1 in the middle of them.
So it's 2 capacitors in series.
Yeah. So should I do it? I don't know if I can get my finger in there. Ooh. Oh, I can. But it has to be my pinky.
Give us a countdown.
Oh, God.
Wait, did you do it?
No.
Oh.
I just don't want to. Okay. I've been shocked. It can't be that bad, right?
No, it's not. We used to shock each other all the time with it.
3, 2, 1. Oh, I felt it. I did feel it. It wasn't that bad at all, but it anything that you feel at that moment. Yeah.
Did you see an arc?
No, but I have with bugs in there. Sometimes I see them spark. And sometimes I see them twitch.
Maybe we could guess the voltage.
I would think it's not that much based on how much or how little that hurt.
But what is it like? I forget what the distance is. It's like 1,000 volts per centimeter or something.
Oh yeah, the dielectric, the breakdown of air is. I think it's 3 million volts. Oh, per meter. That makes sense. I was like, that can't be 3 million volts per inch. Yeah.
So 3 billion volts per meter. So 30,000 volts per centimeter. But it's probably a millimeter or less that it would be arcing, from a bug to the other wire.
Oh.
But doesn't that seem like it should be?
No. It'd be way closer than that. It's like the bug is just barely coming off the thing.
Well, let's say it was, I'm just going to pick a random number, 3 microns.
Okay.
Then it would be a volt.
Yeah.
Right. So.
Yeah. Okay. So we're getting on the order of that. Yeah.
Yeah. Okay. So that might make sense. Mm-hmm. And I don't. Yeah. I mean, you can see molecules glow. Like a single molecule let off a photon. So I don't know why you wouldn't be able to see like 3 microns worth of air breakdown.
Yeah. And maybe it wasn't even a spark. It was just like the bug like glowing or something, a part of the bug burning. Because sometimes it does smell.
So I just opened Reddit, Reddit's R Physics.
Oh, I have a puzzle from Reddit.
Yeah, do you want to do that?
Okay, so the post, I mean, I don't remember exactly what it was, but I think it was like a guy who was like a writer, and he was writing a science fiction book, and in his book, he wanted to have people explore other planets by dropping to the surface of the planet in a sphere that was filled with water. And the people that were going to explore the planet were in that sphere of water, and that's how they were going to survive the impact of landing on the surface of that planet.
Sure. Okay.
So how about we just stop there and just, what do you think of that?
That sounds deadly.
Does it?
It does. Yeah. Especially if it's a sealed sphere.
Okay.
Because I think you're just going to create a ton of pressure inside of the sphere and you're going to feel all that pressure as a human being inside of there and not like it.
So I think my assumption is that water would be an incompressible fluid. I don't know if that changes anything.
Right. I agree. But it doesn't change my thought process.
Okay.
Here's what I'm thinking. Maybe you've ever seen this. This does have to do with some compression, so maybe it doesn't exactly apply. But you ever seen the trick where you fill a beer bottle like 90% with water, and then you hold it and you hit the top of it really hard, and it blows out the bottom?
I've never seen it blow out the bottom. Well, maybe I have, but I think of it as like all of a sudden becoming a volcano of beer at the top.
No. So this is, you can actually like just blow out the bottom of the glass.
Oh, no, I've never seen that. It kind of sounds familiar, but if I ever saw a bottle break, I would have thought it was just because someone hit the glass too hard, not because of like pressure popping it out.
I haven't watched it, but this looks like he's doing what I'm talking about.
Beer bottle breaking tutorial. Oh God, what's the rule for how many seconds into a video before?
I think it's 10%.
Okay, there's a 1 minute and 40-second video. I'm 30 seconds in and I haven't learned anything.
Yeah, if you go to like 1:30.
Okay, of 1:40. Oh, just with your hand. Wow, I thought with a hard, like another beer bottle or something, but just with this hand.
Yeah, just your hand.
Well, I guess, yeah, for it to be a pressure thing, it would have to be something that seals it better than a glass bottle or something like that.
Right. Yeah, so my basic understanding is you hit it really hard and it compresses the small amount of gas that's in it, because I don't think you fill it all the way. And then when you compress...
We're back to the person landing on a planet inside of a sphere of water.
Well, in this bottle thing, the way that it works, I think, is, you hit it really hard and you seal it with your hand, but because you're going quickly, you compress a little bit of the air that's trapped inside, which raises the pressure, and then enough to blow out the bottom of the bottle.
Yeah.
So I don't know if it has to do with the fact that the air is compressing. That is what breaks it out. And my first thoughts on this sphere of water thing is, the same kind of pressure that blew out the bottom of that bottle is going to be affecting you. But if we're assuming a no trapped air inside, I'm not sure if that works or not.
Yeah. So I went back and forth on this for a while. My assumption was you could survive, like assume it's completely full. And then you could survive any fall that you would survive by jumping into a pool of water. Like if you could survive jumping from that height into like an ocean, you would survive falling with the water like onto the surface.
Okay, I think that's semi-fair assumption.
The way it unfolded though is that was completely wrong.
Okay, because the one thing that's confusing me about at least the one thing that I thought of when you said that is you don't have the whole surface tension issue when you're inside the water already that you would jumping out into the water, right? They always say like, oh, falling at the certain height, it's like hitting a brick wall. I guess that doesn't have to really do with surface tension necessarily, though. Could just be...
Yeah, I don't know that surface tension plays a big role. It's there, but I don't think it affects a whole lot.
Yeah, I think it's just, how the velocity that you could travel in that medium. Right, so you're just doing a very quick change of velocity.
Right. Yeah, so let's assume we're neutrally buoyant. So, whatever the water does, that's what you're going to do, essentially. Does that make sense? I kind of just gave it away right there.
Sure. Okay. Yeah. You're floating in the.
Right. So what I thought, even being neutrally buoyant, what I thought would happen is the sphere of water comes to an abrupt stop by hitting the ground. Let's say it hits like sand and it kind of just dies without bouncing or digging too much or anything like that.
Okay.
Water just abruptly stops. I thought you, even being neutrally buoyant, would shoot to the bottom of the sphere.
Right. But yeah, that's not going to happen because it's not compressing.
Yeah. But,
right. Like if you imagine it being a container of gas, of air, and a balloon in the center or something, right?
Mm-hmm.
Then the balloon would go up, you'd predict, when it hit the ground, because all the air is going to go to the bottom. It'll compress itself, but the water not going to compress.
Right. Yeah. I think what would happen is it would be just like you hit the ground yourself, because the water's incompressible. You're going to accelerate with the water, or decelerate with the water, coming to an abrupt stop the second, like as soon as the water does. And it made sense. Someone said, if you're neutrally buoyant, then you're just like any other parcel of water in the sphere, and none of those bits of water are moving around each other. So why would you move around?
Yeah, that makes sense to me. But my question is, though, if you are not, okay, you're not necessarily just a bit of water. You're more like a neutrally buoyant bubble, right? Because you're still breathing. You've got a tank or something on. So, like, let's imagine you put a balloon in water and you hung a weight from it or something. So it's countering the buoyant force of it. So now it's neutrally buoyant. Like, what happens to that balloon?
Well, I think what the people in the thread said is your organs would be smushed, basically, is what would happen. Like your body wouldn't move, but like all the stuff inside of you would be sloshed around. Lungs would compress, like you're saying. Everything would get smushed. Inside of you. Your brain would, probably have a concussion because your head would stop abruptly, but your brain would want to keep moving. Right.
All like your typical impact sort of thing.
Yeah. So it would be just like you slamming into the ground, basically. The water is just an extension of the ground at that point.
Right. So, yeah. So that's kind of what I think. That's what I would have interpreted to happen as well. But what if you opened up the sphere? You had like a hole in the top.
Yeah. So I got confused because I was like, well, if that's true, then how does anyone jump into water? Like, how is that? How is it possible for people to dive into water if everyone's neutrally buoyant? Like, wouldn't you just stop because you're like the rest of the water?
No, because you're able to displace water with your momentum. It's able to push the water away or pile it on top of itself. If it's
exactly. That's like, yeah. So you're saying if it was open, there'd be room for the water to get out of the way and like spill out.
Yeah.
Yeah.
And then in that case, you might be closer with your original thought of you could survive like whatever height you could jump into.
Right. Yeah. So I was thinking the safe way would be to have somebody like suspended over the surface of the water inside the sphere, just like a foot outside of the water. And then the second the sphere hits the ground, you dive into the water just like you normally would.
Well, I think you'd want to like actually be on the surface.
So I thought about that too. Like, what if you're like half in the water, half out of the water? What happens then? Like, or like, what's the limit? Like, what if you're like your nose is the only thing out of the water at that point? Doesn't matter. Or what if you're completely submerged and there's just a hole in the top for the extra water to get out?
Right. Well, so I think if the hole is large enough, I don't know enough about fluid dynamics, but if the hole is large enough, like you can imagine if you put a pinprick in the surface of it, not much is going to change.
Mm-hmm.
But if you get like a large enough hole, then the water is going to like recoil and eject out. And that's going to give you it's going to slow you down. It's going to change your impulse because you're going to be deaccelerating over a longer period of time. So I think you'd want to be close to the top or at the top of the water so you have the largest distance to slow yourself down over.
So now we're getting to where I initially started answering this, and then I was shown I was wrong because if it was completely full and sealed, it wouldn't work. But let's say it's an open top or there's some opening to let the water move out of the way. I was thinking you start on like the side, like if you look at a globe, like you're on the equator, and then when you hit the water, you're on the side of the sphere and you end up like spiraling around, like doing like loops to like get the longest distance to slow yourself down through, rather than just a straight line to the bottom of the sphere.
How would you get propelled in you're talking about like a helix or something?
I don't know if it would necessarily be a helix or just being pressed along the outside of the sphere, just like doing circles like within the sphere.
But why would you go in circles?
You start on the side of the sphere and then the sphere stops and you're having your downward momentum with the normal force of the wall of the sphere pushing you towards the center of the sphere.
I see. And I was thinking of like a lateral, like parallel to the ground type of circle.
No.
So you're talking about like a vertical one.
Yeah, like a stand-up like bike wheel or something like that shape.
Right. As long as you don't fly out the top.
Yeah. So I don't know where the hole is. Yeah, exactly. Or at least give yourself enough distance to go through like a semicircle or something like that.
I think
that'll give you more distance to slow through before, rather than starting at the top and just have the diameter of the sphere.
Right. I think there's another issue with the top as well, particularly because it's a sphere. Like I have this vision of like, if you started like with your head out of the water, let's say a little bit, or like some part of your body out of the water, then when it hits the water that gets ejected out of the sphere, like I see it like being pushed, like jet propelled at your face in my like mind simulation that I'm running right now. And I don't see that being pleasant.
Well, maybe it doesn't have to be open. It could still be sealed, but there's just maybe a little bit of air, just enough space without water that the water can move out of the way. But then you're building up a lot of pressure. We're back to this exploding beer bottle.
Right. I think
maybe. I don't know.
I think your way works well for a sphere. I think the other, an easier maybe way to think about it in terms of like, how is the water going to escape, would be if you had like an open cylinder rather than a sphere.
Yeah.
Then I think pretty easily you could say like you want to be up as high as you can in that, and the water is going to. I think you'd still get hit by a pressure wave though. That like when it smacks the ground, that's going to part some impulse in the water that's going to create a wave that's going to travel through you. And if that's enough pressure, it'd be like a bomb going off, right? Like,
well, so here's an interesting question. We're assuming water's incompressible, but it's not actually incompressible, right?
Right.
If something is actually incompressible, I don't think sound like pressure waves can propagate through them. I think the sound is the in the wave function is describing the difference in pressure at different points.
Right. Yeah, that's true. But I mean, realistically, I think there would be a pressure wave propagating from the bottom up. Right. I think maybe we could put it in a different setting, though, right? Who cares if you're being dropped from the sky? Like, let's use another force. Let's say you put a bomb at the end of it.
Yeah.
At the bottom, you're just sitting there, and there's a bomb beneath you. that releases the same force that would be if you hit the ground. Like, I think if you put it in that scenario, like, your intuition is going to say, like, yeah, that would probably hurt me. You know, like, I would feel the pressure wave, just like, I mean, even if you do it in air, right? And a bomb goes off near you, the concussive wave can kill you.
Right.
So I think, like, you'd have a similar thing, but in water. Now, I don't know how water will change the pressure of that wave, though. Because I think Mythbusters did do a thing where they, like, tried exploding a bomb in water to see if you'd live.
Really?
Yeah. I don't remember what the result was. And I don't know if their bomb was in water or out of water. But you were definitely in water.
Yeah.
Mythbusters, bomb in water. And this is how I got on the FBI watch list. Okay, I think this is diving underwater when the bomb is exploded above water. It says diving underwater can protect you from an explosion. And it says plausible.
Yeah, I could see that.
Okay, a person can survive a large underwater explosion at a distance of 50 feet. Busted.
Oh. So they can't survive.
Yeah, so the other plausible one was the bomb is out of water and you are you go underwater. Yeah. This is if the water is underwater. But here's an interesting: a person can increase his chances of surviving underwater explosion by floating on his back at the surface. So floating on top of it does give you the potential ability to survive. So maybe you want to float on top of your cylinder of water or your sphere of water.
I can't immediately figure out why that would be the case.
Right. What would be the difference between...
I guess you have less of a resistive force, so you can just move with the water more easily, just to, like, go with the flow, kind of?
Yeah. Yeah, because you're not immediately being impacted by the water.
Yeah, I guess I don't know what kills you if you're underwater and the bomb goes off. Is it because one front, like say you're like in a standing position underwater and the bomb is in front of you? Are you killed because the front of you is feeling a much higher pressure than the back of you and you're kind of squeezed? Or I guess not higher pressure in front, lower, and back, but like basically you're squeezed in the water because you're trying to get out of the way of the compression wave, the shock wave that's coming towards you.
Yeah,
and you have a whole bunch of water at your back, so you can't move, so you're just kind of squeezed and killed.
I mean, I think it's the compression wave, but I don't know. Yeah, the nature of how that does that. If that just creates like a high pressure zone that
right.
when your body enters that zone, now you're in that pressure and that just squeezes you,
right?
Or if it's
because then if you're at the surface, all of a sudden that pressure front hits you, you're just going to be pushed into the air, which you're not going to get squeezed.
Yeah, and there must be some sort of you'll get some reflection off of the boundary, and what else would happen? Velocity of the wave would change a little bit, so that might affect something. But based on this not being able to, this is as a large underwater explosion. I don't know what qualifies as large.
Yeah.
But based on that, I'm going to say you're not going to survive the falling, even if it's open. I don't think you'd survive. But I'm kind of curious, like what would be the terminal velocity of like a sphere that could hold one person?
The terminal velocity?
Yeah. Okay. If you had a sphere that could hold your average person
Mhm.
like single person inside of it.
I can tell you the original Reddit post was 20 meters in diameter.
Oh, okay, 20 meters. That's
a large
sphere.
Yeah. And he initially had them like suspended in the dead center, and then everyone was like, no, they need to be like at the top. And then I said on the side.
Yeah, this whole time I'm imagining like a sphere my arm width apart. Yeah, so let's see.
It's probably a formula for this.
Yeah, velocity of a sphere. Okay, I have your general equation here is terminal velocity is equal to root 2 mg over the density of the fluid times the cross-sectional area times the drag coefficient. And for a sphere, the drag coefficient is 0.47. That's interesting that the drag coefficient is different for a half sphere and a sphere.
Huh. I guess, yeah, some sort of like turbulent thing in the back.
Yeah, it must be. Okay, so 20 meters, let's see, 4/3 pi times...
I must have done something wrong. What's the drag coefficient for a sphere?
0.47.
Oh, I wasn't that off.
That's the volume. And it's what? Water 1 kilo? It's not 1 kilo per cubic meter. It's 1 gram per cubic centimeter, right?
Yeah, it's a ton per cubic meter.
Okay, so I'll times this by 1,000 then. So our mass is 3.4 million kilos. Is that right? 4/3 pi r cubed is the volume of the sphere, right?
Mm-hmm.
Okay. now times that by 1,000 to get kilograms. Because the density is 1,000 per cubic meter. And you get, okay, we can call it 3.4 million kilograms is the mass of the thing.
Uh-huh.
We can assume the extra, I rounded up a bit, maybe that's the weight of the shell.
What's the area?
1,256.6.
1250.
Yeah, that works.
And density of air?
Oh wow, that's pretty convenient. 1.225 kilograms per cubic meter.
Let's assume on Earth. All right, so this calculator gave about 300 meters per second.
Okay. What is
which
that?
is 680 miles an hour.
So 600 meters per second, that's our V. Our M is 3.4 million.
No, 300 meters a second.
Oh, it's 300. Oh, so, okay, 300.
680 miles per hour.
3.4 E6 times 300. Oh God, there's too many zeros in that. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 trillion. 1,200,000,000 or 1,020 billion is the momentum in whatever momentum units are.
Yeah.
Okay, and then that goes to 0. What's the equation for impulse?
For average force. Are you trying to find the force?
Yeah.
Yeah, so if you just make an average force, it's just force times time.
Okay.
So divide the momentum by an amount of time.
Okay, and so we're going to say an impulse is also the change in momentum, right? So we're going to say the momentum goes from that to 0 because you stop. Okay, so then, yeah, it's that divided by time. And I don't know what a good time would be. Even if we just said 1 second, right? Just to make simple.
That's a long time, but yeah, let's go with 1 second.
I know. I mean, because if we made it 100 milliseconds, maybe, that just multiplies that number by 10 to make it 10 trillion newtons. How many pounds is that? Oh, it's divided by like 2.2, right?
No, that's
times
the kilogram.
Times by 2.2.
No, neither. That's the kilogram to pound conversion.
Oh, that's right. Okay.
Yeah, but it is almost 2.2. Let's see, that's million. Yeah.
Okay, so that's according to this, that's 2.2 trillion pounds.
Google didn't even do it.
Yeah, I could get Google to do it either. It's like that number's stupid. Doesn't make sense.
An aircraft carrier is 100,000 tons. So basically that force is the weight of 10 aircraft carriers.
I want to compare it to a nuclear bomb.
But that's, what do you mean?
Like
the force?
Yeah. When they say like it's don't they how do they weigh it or like give the force of it? Like 2,000.
Oh yeah,
20,000 tons of TNT. What does that mean?
Of TNT, like weight of TNT.
Oh, okay. That doesn't actually tell you what the 84 tetrijoules.
So okay, well let's work with energy. How much energy is there? Because it's taking all that kinetic energy to zero.
Right.
I'm getting my calculator out. Real Calc on Android. It's the best. Yeah, so 1.5 times 10 to the 11th joules. 0.1 terajoule.
Okay, so it's much weaker than a nuclear bomb.
I would expect so. I don't think we could just drop spheres of water. That would be equivalent to a nuclear bomb. Why do we waste all this money on the Manhattan Project? We could have just dropped 20-meter square spheres of water. Yeah, 20-meter diameter radius. I don't know, squares of water. Well, spheres of water.
Because, Derek, then we have to create something that has the energy to carry that up into space. Yeah, so...
Okay, what you just said is an interesting point. Like, that's a huge benefit to bombs, is that it doesn't take the amount of energy of the bomb to put the bomb in space, like to move the bomb.
Right, yeah. That's the whole magic of E equals MC squared.
That's something I hadn't thought of, is that you don't need the energy of the bomb to create the bomb. I don't know why I never thought of that. Same with, I guess, gunpowder.
Yeah.
Same with everything. I don't know why that's shocking to me, but yeah.
You just hadn't put it into this perspective.
Yeah, like not everything is like, yeah, sure, energy is always conserved, but like we don't have to make the energy. I guess that's what basically I've just realized what natural resources are. That's all.
Yeah. Yeah, so I'm kind of, so we are the first test of a fission atomic bomb, that was the one that was 84 terajoules. So we are 840 times smaller than that. That's, I don't know if the tons scale the same way, because otherwise I'm wondering if we can just say 20,000 tons divided by 840 would be 23 tons of TNT if it scales linearly like that. And I don't know that it does, but maybe for the sake of right now, so that would be, what did I say? 23 tons of TNT would be, so it's like, I think enough to kill you. like if that explosion went off at the...
Well, I think what you're doing is figuring out if you were underneath the sphere when it landed, would you die? And I think the answer is unequivocally yes.
Well, right, but
I don't think we needed to do the physics to figure that out.
But it hitting the ground, like if you were inside the sphere, right? before.
Oh, I see what you're doing. You're figuring out the quote unquote explosion inside the water.
Yeah. If you were inside the sphere and I, sealed it and you couldn't see where we were, you wouldn't be able to tell if I dropped you onto the Earth or detonated 80 or 23 tons of TNT outside your sphere. You would feel the same thing, I think, or, roughly something along those lines. And I think you die either way.
Yeah. If I learned anything from Inception, it was that falling over a bridge and a bomb going off on the floor below you is the same sensation.
Falling
Isn't that what they did in the movie?
I don't remember exactly. Yeah. Oh, yeah, that's right. Yeah, because they were like,
they needed a kick, and they were like, the one was the van going over the bridge, like into the water, and then the other was the guy rigging up explosives in the hotel, like a different floor above or below or something like that.
Right. That was like, so they didn't realize what was happening or something?
No, it's to wake them up, to get them out of the dream.
Oh.
You need a kick.
Right. I don't know if that means that it feels the same necessarily, but
I don't know. I trust Christopher Nolan and his scientific research.
He did his math. He got Leonard Susskind on there.
Exactly. Did he do that one? Was Christopher Nolan the Interstellar guy?
I think so, wasn't he?
I think you're right. Yeah.
Yeah. So I'm gonna answer your at least 20-meter thing with unequivocally. You're dying. I think no matter what.
Some way you're gonna die.
Yeah. Whether it's open or closed or half filled with water, half filled with air. I think you're dying.
I have a mosquito. I'm about to use the racket.